In the previous segments, we have seen how the planning problem can be solved by searching for solutions, but we've set up two completely different types of search spaces. One was the state space and one was the plan space. But both approaches really solved exactly the same problem. In the next segment, we will modify the problem itself, so the approaches we've seen so far are no longer applicable. Previously, a planning problem contained a goal, and a goal was a condition on a world state that we want to achieve. Now we will look at tasks. Tasks are things we want to do. You may remember the example from the introduction, going on a holiday. That would be a task. And I've already mentioned then that this would be difficult to describe as a goal because we want to end up in the same state in which we started. So we will now look at tasks and task networks, which are the essential components we're dealing with in hierarchical task network planning. So we will start by defining simple task networks. Simple task networks are really a simplification of the more general approach, which is called hierarchical task networks, or short HTN. You've already heard about HTN planning in week 1, when my colleague Austin Tate was talking about planning in context. But let's start from scratch here. A lot of what we've seen so far carries over into task network planning. For example, we have terms that can be either variables or constants to describe the objects in our domain that we're dealing with, and we have literals that express propositions that are either true or false. We also have operators that describe types of actions that we can execute in our domain, and of course we have their instances, which are actions which we want to execute. The semantics is still based on state transition systems, so we also have a state transition function that describes how the world evolves when we execute our plan. And of course we still have plans, which are the solutions to our planning problems. But there are a number of new components that we need to consider in task network planning. And the first component are of course the tasks themselves, the things that we want to do in our domain, like going on a holiday or fixing a car or learning something on this course. Simple tasks correspond to actions directly, but of course we often deal with tasks that are more complex. Like going on a holiday is rarely a task that we can consider as directly executable. The next new component are the methods that describe ways in which we can do our tasks. And this description usually consists of a number of subtasks that together achieve some more complex task. And these subtasks in itself can be organized, they can be ordered with respect to each other, for example, and thus form a task network. So what we will do now is formalize tasks, methods, and task networks, and then define planning problems based on these concepts and what solutions look like, and finally algorithms that solve this type of problem. Let me illustrate all this with another example taken from our DocWorker robot domain. As you can see in this picture here, this is a very simple problem. We have a single location at which we have one crane, and we have 3 piles and 3 containers. Currently, all 3 containers are in the first pile, and we want to move these containers to the third pile. So our task is to move a stack of containers from pallet P1 to pallet P3, and we want to do this in such a way that the order of the containers is preserved. Clearly, this is a task that we cannot achieve with any of the actions we've previously described. It is a more complex task. We could, of course, describe this as a planning problem that we've seen so far, but here's a set of informal methods that we can use this type of problem in general. And I will start at the bottom here. So the first method we can have is to move a container from one pile to another pile, and of course we can only ever move the topmost container. So we have a method for moving the topmost container, and we say this method is simply a take action followed by a put action. So we have 2 actions that are ordered with respect to each other that make up this method of moving the topmost container. So this is a very simple method that simply groups 2 actions together. A more complex method is to move the whole stack, and we can do that by repeatedly moving the topmost container from one stack to another. We must do this until the stack is empty, and if we do this, of course a side effect is that we reverse the order of the containers in our new pile. And we can fix that last problem by having a third method which says we move via some intermediate stack. So we first move our stack to an intermediate stack, and that reverses the order of the stack, and then we move it to the final destination and we reverse the order again. So these three methods taken together describe a way in which we can move a pile of containers from one pallet to another pallet, respecting the order of those containers. I hope you can see that this approach is much more akin to the way humans solve problems, and this is by hierarchical decomposition and identifying abstract concepts. Here we've identified the more abstract concept of a stack that didn't exist in our previous domain description. And now we can formally define what we mean by a task. And the first thing we need is a set of symbols that we can use to give unique names to our task. And these are the task symbols given by the set TS, consisting of T1 through Tn. Now, our operator names, which are the names of the operators we are using, must be a subset of our set of task symbols. And if for a given task symbol we also have an operator name that corresponds to this task symbol, we call this task symbol a primitive task. And then we have the non-primitive task symbols, which are simply those task symbols for which we don't have corresponding operator names. A task, then, is simply a syntactic expression of this form. It consists of a task symbol Ti, which can be either a primitive task symbol or non-primitive task symbol, and it consists of a set of arguments R1 through Rk, which are the terms representing objects that are manipulated by this task. This is of course very similar to the way we've defined operator names, and that is not a coincidence. And similarly, we will define ground tasks as all those tasks for which all the parameters are ground, which means they are actual objects and not variables. A ground operator was called an action, but we don't have a special name for ground tasks here. This means we have four types of tasks here. Tasks can be primitive or non-primitive, and they can be ground or unground. And to relate tasks to actions, we can make the following definition. Suppose we are given an action A, which is described by the name op C1 through Ck, where op is an operator name, and C1 through Ck are constants representing the parameters of this action. Remember, it's an action, so it's fully ground, so these must be constants and not variables. We can say that this action accomplishes a ground primitive task described by the expression Ti R1 through Rk in a state S if the following two conditions hold. The first condition states that the syntactic expression that describes the action and the syntactic expression that describe the task must be the same. So what we must have is that the name of the action, as given here by op, must be the same as the task symbol, and of course it's a primitive task, so we have an operator name that corresponds to it. And we must have that all the arguments must be the same. So the first constant must be equal to R1 and so on. And of course, because these are all constants, R1 through Rk must also be constants, otherwise they couldn't be equal. So the first condition is that the syntactic expressions for the two, action and task, must be the same. And the second is that the action A must also be applicable in the state S. So what this gives us is a way of accomplishing very simple tasks, namely those tasks that are ground and primitive. But we can't accomplish unground or non-primitive tasks yet.